Welcome back to G Fun Facts Online. Today we are leaving the familiar ground of Earth, bypassing the rusty plains of Mars, and even skipping past the gas giants that act as the sentinels of our solar system. We are going deep into the cosmos to answer a fundamental question about how worlds are built. Specifically, we are going to talk about moons. In our own solar neighborhood, moons are often more fascinating than the planets they orbit. You have Europa and Enceladus with their subsurface oceans, promising potential biospheres beneath miles of ice. You have Io, the most volcanically active body in the solar system, turning itself inside out with lava. And you have Titan, a world of methane lakes and thick orange smog. For decades, astronomers have looked at this diversity and wondered, is there a universal recipe for making a moon system? Do they all start the same way, or is every system a unique chemical experiment cooked up by the universe? Until now, we have only been able to guess, using the fossilized remains of our own solar system as clues. But that era of guessing is over. Thanks to the James Webb Space Telescope, or JWST, we have finally peeled back the veil on a satellite nursery in a distant star system. What we found there has completely shattered our expectations and rewritten the textbook on how moons evolve. We are looking at a world known as CT Chamaeleontis b, or CT Ch b for short, and the story it tells involves a chemical factory teeming with organic molecules, a massive divergence from the water-rich history of our own system, and the tantalizing possibility of life existing in oceans of oil. Let us start by setting the stage. To understand the magnitude of this discovery, we need to understand the target. We are traveling approximately 625 light-years away from Earth to the southern constellation of Chamaeleon. Here lies a star system that is essentially a stellar toddler. The primary star, CT Chamaeleontis A, is just 2 million years old. To put that in perspective, our Sun is about 4.5 billion years old. This star is still a T-Tauri star, which means it is variable, active, and hasn't quite settled onto the main sequence yet. It is still surrounded by the chaotic debris of its birth. Orbiting this young, tantrums-throwing star is our object of interest, CT Cha b. This is a fascinating object that straddles the line between a giant planet and a brown dwarf. It is estimated to be about 17 times the mass of Jupiter. That is massive enough to burn deuterium in its core, but it likely formed like a planet. What makes CT Cha b the perfect laboratory for us isn't just its size, but its location. Most of the exoplanets we study are hugging their parent stars, blinded by the stellar glare. CT Cha b, however, is a loner. It orbits at a staggering distance of 440 to 500 astronomical units from its star. For comparison, Pluto orbits the Sun at an average of 39 astronomical units. CT Cha b is sitting in the deep freeze of the system's periphery, thermally and dynamically isolated. This wide separation is the key. It allowed the James Webb Space Telescope to resolve the planet as a distinct object, separate from the blinding light of its parent star. But Webb wasn't just looking at the planet. It was looking for something much more subtle. It was hunting for the circumplanetary disk. Let's break down what that is. When a giant planet forms, it grows by pulling in gas and dust from the larger disk surrounding the star. As this material falls onto the planet, the laws of physics, specifically the conservation of angular momentum, cause it to spin up and flatten into a mini-disk surrounding the planet. This structure, the circumplanetary disk, or CPD, is the satellite nursery. It is the reservoir of material from which moons will eventually coalesce. Just as planets form from the dust circling a star, moons form from the dust circling a planet. For a long time, our models of these disks were biased by what we see at Jupiter. The Jovian moons show a clear density gradient. The inner moons are rocky, and the outer moons are icy. This suggested that the disk they formed from was water-rich, allowing ice to condense and become the primary building block. So when astronomers pointed the mid-infrared instrument, or MIRI, on board the JWST at CT Cha b, they expected to see the spectral fingerprints of silicates and water vapor. They expected a standard, water-rich recipe. But the universe had a surprise in store. The spectrum that came back from CT Cha b was unlike anything seen in a planet-forming environment before. Instead of water, the light from the disk was dominated by intense emission lines from carbon-bearing molecules. It was a chemical inventory that read like the manifest of an organic chemistry lab. They found acetylene, a highly reactive hydrocarbon associated with high-energy processes. They found diacetylene and propyne. Most shockingly, they found benzene. Benzene is a stable ring of 6 carbon atoms and is a fundamental building block for polycyclic aromatic hydrocarbons, or PAHs. These are complex organic materials often cited as precursors to prebiotic chemistry. Along with these, they detected methane, ethane, and hydrogen cyanide. But conspicuously absent from this chemical soup was the one molecule everyone expected: water. While the parent star's larger disk was rich in oxygen-bearing molecules like water and hydroxyl, the planet's private disk was dry and choked with hydrocarbons. The ratio of carbon to oxygen in this satellite nursery was significantly higher than 1. In astrochemistry, that is a tipping point. It means there is more carbon than oxygen available in the gas phase, and that radically changes the types of rocks and ices that can form. This presents us with a massive mystery, something astronomers are calling the Great Divergence. How can a planet and its potential moons be made of completely different stuff than the star they orbit? Remember, this system is only 2 million years old. This chemical split happened fast. There are a couple of leading theories to explain this. The first is the pebble accretion hypothesis. This involves how solid material moves through a star system. In the cold outer regions, carbon and oxygen are locked up in icy grains we call pebbles. Oxygen is usually locked in water ice, while carbon is locked in more volatile ices like carbon monoxide. The theory suggests that as these pebbles drift inward, they hit different temperature boundaries. If CT Chamaeleontis formed at a sweet spot where the oxygen-rich water ice was frozen onto large pebbles that drifted past the planet too quickly to be captured, but the carbon-rich gas was moving slowly enough to be eaten by the planet, you get a filter effect. The planet essentially breathes gas that has been filtered of its water by the physics of dust transport. Another possibility is the soot line. This idea revolves around heat. The detection of benzene suggests active soot chemistry. As dust grains fall into the circumplanetary disk, they get heated up. CT Chamaeleontis is young and hot, glowing at thousands of degrees. If the disk is hot enough to destroy oxygen-rich silicate grains or water ice but keeps carbon in the gas phase, the local chemistry flips. The intense radiation drives photochemical reactions that destroy water molecules while synthesizing complex hydrocarbon chains. It effectively turns the satellite nursery into a factory for organic smog. So what does this mean for the moons? If moons are forming in this disk right now, and the presence of such a massive disk suggests they will not look like the moons of Jupiter. Europa and Ganymede are water worlds, silicate cores wrapped in ice. But the moons of CT Chamaeleontis would be carbon worlds. Instead of water ice, their mantles would be composed of frozen methane, ethane, and complex tar-like organics called tholins. Their rocks might not be silicates like on Earth, but carbides. Minerals where silicon bonds with carbon. We actually have an analog for this in our own solar system, Titan. Saturn's largest moon is the only moon with a thick atmosphere, rich in nitrogen and methane. It has liquid methane lakes and rains hydrocarbons. Titan is a carbon world in a system otherwise dominated by water ice. The discovery at CT Chamaeleontis suggests that Titan-like worlds might not be rare anomalies. In fact, for massive planets orbiting far from their stars, carbon-rich satellite systems might be the norm. The Titan-forming channel of moonbirth might be just as common as the Europa-forming channel. This naturally leads us to the question of habitability. When we search for life, we usually follow the water. We look for liquid oceans because water is the solvent for life as we know it. But the chemistry of CT Chamaeleontis challenges our geocentric view. The ingredients for prebiotic chemistry are present there in staggering quantities. Benzene and PAHs are the scaffolding for complex biology. Hydrogen cyanide, which is deadly to us, is actually a key precursor for amino acids and nucleobases, the building blocks of proteins and DNA. While the disk appears dry in the gas phase, that does not mean water is entirely absent. It might be locked deep in the cores of forming moons. But even without water, could life arise? If moons at CT Chamaeleontis have liquid surfaces, those liquids would be hydrocarbons like methane. While terrestrial biology cannot function in liquid methane, scientists have modeled hypothetical cell membranes called azotosomes made of nitrogen and carbon that could function in such cold, non-polar solvents. A satellite system formed from this disk would be a planetary-scale laboratory for organic synthesis, potentially hosting weird life that relies on oil rather than water. We also have to appreciate the technological triumph here. Detecting the chemical composition of a circumplanetary disk is incredibly difficult. It is like trying to analyze the smoke from a single candle sitting next to a spotlight, from miles away. The glare of the primary star is a formidable obstacle, and the disk itself is a tenuous veil of gas mixed with the light of the planet. The team used the MIRI medium-resolution spectrograph and sophisticated data processing to subtract the star's light and isolate the thermal emission of the disk. The specific emission lines of molecules like benzene are fingerprints that cannot be faked. This success proves that JWST can dissect the formation environments of non-transiting worlds, opening a new frontier in exoplanet science. Finally, this discovery forces us to look at our own solar system with fresh eyes. Why are Jupiter and Saturn so different from CT Chamaeleontis? It likely comes down to migration and history. Jupiter and Saturn likely formed closer to the Sun and migrated, interacting with a richer supply of oxygen-bearing ices. CT Chamaeleontis is stuck in the stellar periphery. It is also much more massive and hotter than Jupiter ever was, driving that soot chemistry we discussed. By comparing these systems, we are building a periodic table of planet formation. We are learning that there is no single way to build a moon system. There is a spectrum, ranging from the oxygen-rich, icy nurseries of the inner solar system to the carbon-rich, soot-filled nurseries of the outer fringe. The detection of the disk is just the beginning. The next steps involve using the ELMA telescope to see the cold dust grains, giving us a 3D picture of the nursery. We will also look for kinematic evidence, watching how the gas moves to see if massive moons are already clearing gaps in the disk. But for now, the takeaway is clear. The universe is far more creative than our models often give it credit for. We used to look for another Europa, assuming water was the universal currency. Now we know that nature is equally adept at minting super titans, worlds born from smoke and fire, swimming in hydrocarbons. The era of exomoon characterization has arrived, and it has begun not with a whisper of water, but with a symphony of carbon. Thanks for listening to this deep dive into the cosmos. Stay curious.